Angiotensin-Aldosterone system, sodium-potassium balance, and diuretics. So to overview the renin-angiotensin-aldosterone system, the kidney is going to be secreting renin in response to either sympathetic drive or decreased pressure or decreased salt delivery. All right. So the sympathetic drive comes in states of low blood pressure. The sympathetic nervous system kicks in to try to raise the blood pressure, and that's sort of a short term and has a bunch of short term actions that it does. But one of the ways that it transitions the nervous system will translate its short term response to a long term response is by signaling for the juxtaglomerular cells to secrete renin. So when we talk about, and we'll look at the juxtaglomerular apparatus on the next slide, but what I want you to visualize is that there are cells in the distal convoluted tubule that will detect the amount of salts and chloride. It's principally the chloride that they're detecting using their cilia. So they have these projections coming out of their cell membranes that enter the sort of the tube of the nephron, and it's sampling and it samples the fluid. And when there's low salt, it takes that to mean that there's low water because water follows salt. And because there's low salt, that implies there's low water, and that implies the kidney is not filtering as well as it should. So how does the kidney rectify that? By increasing pressure in the glomerulus, to increase the amount of hydrostatic pressure so that the fluid gets forced into the tubules. So that's why decreased pressure and decreased salt are going to trigger the release of renin from the non-macula densa cells of the juxtaglomerular apparatus. All right. So either in response to low blood pressure from the nervous system, or in response to detecting low blood pressure, or in response to low salt delivery, the kidney is going to secrete renin. Now, renin is going to cleave angiotensin. So renin is going to break down angiotensin into angiotensin 1, angiotensinogen into angiotensin 1. And it's important that you know that angiotensinogen 1 is made in the liver. Angiotensinogen is made in the liver. And ACE, while it's present on blood vessels, angiotensin converting enzyme, it's predominantly acting in the lungs. All right? So angiotensinogen is made by the liver, and ACE is made by the lungs. And ACE is going to convert angiotensin 1 into angiotensin 2, and then angiotensin 2 is going to have a number of actions. All right? Angiotensin 2, for starters, is going to increase the systemic vascular resistance. All right. It's a direct vasoconstrictor, and that has the goal of increasing arterial pressure, which will increase blood volume and cardiac output. And remember, the initial stimulus was low pressure. So by the end of this feedback loop, pressure has been increased. The other action of angiotensin is going to be to get the brain to release all antidiuretic hormones. So the posterior pituitary, so from the posterior pituitary gland, the brain is going to release the arginine vasopressin or antidiuretic hormone. They're the same thing. You might hear different names. So you'll either see ADH or AVP. They are the same thing. Adrenal cortex is going to be acted on by the angiotensin 2 to cause the release of aldosterone. Okay? So the adrenal cortex releases aldosterone under the stimulus of angiotensin 2 or on its own if there's high levels of potassium. And the reason for that is that aldosterone reabsorbs sodium at the cost of potassium. So in states of high potassium, those sodium channels, you send out a sodium and you bring in a potassium. It's not the NAK ATPase, but we'll talk more about the mechanism later. The main overall point being aldosterone is going to promote sodium reuptake and promote potassium secretion into the tubule to be lost in the urine. All right, so over here we're looking at the juxtaglomerular apparatus. And that's sort of what I want to show you is here's the glomerulus, here's where it filters, you have your loop of Henle, and then over here is the distal convoluted tubule. And you can see anatomically, at the level of the histologic anatomy, the distal convoluted tubule sort of overrides, or not overrides, or runs beneath the afferent arteriole. all right, such that the afferent arteriole enters, and the efferent arteriole exits, and the distal convoluted tubule is right here. And what this distal convoluted tubule, what's important about it is on this side you have the macula densa cells. These are the ones that are detecting the salts. So when salt is low, they're going to release prostaglandins to stimulate granular cells to secrete renin. All right, so the macula densa detects salt levels and it will signal the granular cells to secrete renin. This secretion of renin is very important. All right, because of all the mechanisms. Because without renin, you do not get angiotensin. All right. And over here, we just see the capillaries of the glomerulus. You have the mesangium here. Not too important for our discussion today, but just to orient you. So you can see here's the glomerulus. It's feeding into the proximal tubule. I want you to imagine the proximal tubule, you're coming down and then you're coming back up. And as you come back up in the form of the distal convoluted tubule, you now have a sodium chloride sensor called the macula densa. And that sodium chloride sensor, when it detects low salts, is going to signal the granular cells to secrete renin. All right, so there are a few transporters that I want to highlight. First of all, sodium bicarbonate is reabsorbed in the proximal convoluted tubule, and that's the target of carbonic anhydrase inhibitors. The ascending loop of Henle is targeted by loop diuretics, and that's going to be important. I want you to notice the electric neutrality of these transporters. So bicarb is negative, sodium is positive, so zero net charge. One sodium, one potassium, two chloride, zero net charge. All right, you come over here, a sodium chloride symporter. This is what angiotensin 2 acts on. So angiotensin 2, not only does it increase sodium reabsorption in the proximal convoluted tubule, it increases the activity of this symporter. All right, you have to know that. It's important. So thiazide diuretics are going to target the sodium chloride symporter, and note again the electrical neutrality. The potassium sparing diuretics, the reason they're called potassium sparing, we'll get into in a bit. But notice here, you have sodium coming out, but there's no negative charge going with it. Instead, you have a positive charge coming into the tubule. So you pull sodium out of the urine and you're pushing potassium or hydrogen into the urine. And that maintains electric neutrality. So remember, what's one of the stimuli for releasing aldosterone? Angiotensin 2. But what's the other one? Increased potassium. And the reason why is because you can unload potassium at the distal, this is called the aldosterone sensitive distal nephron. So in the aldosterone sensitive distal nephron, you can unload excess potassium. All right, you can unload the excess potassium. So that's why high potassium is going to be a direct trigger for aldosterone, independent of angiotensin 2 signaling. All right, so and over here we have where vasopressin is going to act through V2 receptors. They're called V2 receptors. And there's going to be aquaporins. So if this is the cell, sort of the collecting duct membrane, and this is the urine side, on this side, let's say, I'm going to label this as lumen, L for lumen, and cytosol for the cells on either side. The aquaporins aren't inserted into the membrane. And remember, aquaporins are what they're water channels. So the aquaporins aren't actually in the membrane of the collecting duct by default. By default, they're just sort of hanging out. All right, they just sort of hang out until arginine vasopressin binds its V2 receptor. And when it binds the V2 receptor, so again, remember, pretend this is cell membrane. These are preformed vesicles containing the aquaporins in blue. So they're hanging out in vesicles. All right. What's going to happen is that when arginine vasopressin binds to the V2 receptor, these vesicles are going to fuse. They're going to fuse with the cell membrane, and the aquaporins will now be along the plasma membrane, positioned such that water can now cross. All right? So usually the collecting duct is relatively impermeable to water, but in the presence of arginine vasopressin or antidiuretic hormone, do the same thing. When it binds to the V2 receptor, preformed aquaporin vesicles are going to insert into the membrane such that water can now cross. And I cannot emphasize enough that water follows salt. In the absence of an impermeable membrane, water follows salt. Why? Because water goes where ions go. For the extracellular compartment, sodium is the primary ion. So, if sodium is the primary ion defining the distribution of fluid in the extracellular compartment, the water will go where the sodium goes. Water goes where sodium goes. Water goes where sodium goes. This is a very important principle. All right, so let's talk about some situations. What happens in the body when you have low sodium, or what, and in other words, water, because water goes where sodium goes, and normal potassium? All right, so the body wants to go back to homeostasis. And how is it going to do that? It wants to absorb a maximal amount of sodium while excreting only a small amount of potassium. All right, so you have volume depletion because you have low sodium and low water. Less sodium and water is going to be filtered into the glomerulus. All right, so less gets filtered into the glomerulus, and then about 2/3 of that is reabsorbed, and then it goes through the ascending loop of Henle, where a lot more of the salt is reabsorbed, and then it is detected by the cells of the macula densa. All right, the cells of the macula densa are going to detect the low sodium and water, and they're going to cause the release of renin from the granular cells. All right, so this volume depletion is going to lead to decreased flow, which is going to be detected as decreased signal transmitted by the cilia of the macula densa. And that causes the signal net cascade that releases renin. All right, now that we have renin, angiotensinogen is going to be cleaved to angiotensin 1, and angiotensin 1 will be cleaved in the lungs to angiotensin 2. All right, angiotensin 2, first of all, is going to increase reabsorption at this point here. All right, it's going to increase the efficacy of these sodium chloride symporters. All right, and it's going to also cause ADH and aldosterone. Okay, now because of the ADH, the preformed vesicles that are hanging out in the cytosol of the collecting duct cells are going to merge with the membrane. They're going to merge with the membrane, and now water is going to be able to be reabsorbed due to the presence of ADH or AVP. You can see it both ways. It's the same thing. Angiotensin 2 is going to, like I said, increase the reabsorption in the proximal convoluted tubule and in the distal convoluted tubule through the sodium chloride. In the distal convoluted tubule by the sodium chloride channels, it just increases overall the reabsorption in the proximal tubule. All right, and that's very important with regards to potassium balance. It's very important that you understand that in the presence of angiotensin, this sodium gets more absorbed. All right. Now, the fluid that comes after the sodium chloride channels is going to have relatively less salt because it went through this reabsorption, then this reabsorption, and because of angiotensin, it's going to be reabsorbed here at the sodium chloride symporter. So the fluid that actually gets to the region where aldosterone acts is depleted of sodium. Most of the sodium's already been reabsorbed. So this region has all the principal cells. That's where aldosterone acts at. So aldosterone is elevated, right? The aldosterone is elevated because we had angiotensin 2. However, it won't have that much, even though it upregulates these channels. These are called ENaC. I know it's drawn here like a antiporter, but that's not actually the case. What's happening in the principal cell is that aldosterone, first of all, it upregulates the sodium potassium pump. So if this is the sodium potassium pump, it upregulates it so you can build more of a concentration gradient, but we'll come back to that. The second thing it does, it increases the number and activity of, because it's a steroid hormone. Aldosterone is going to come in. It's going to come in. It's going to it's going to go through a series of events. And it's going to be activate transcription factors, and it's going to lead to more expression of epithelial sodium channels, ENaC. All right. Actually, I should draw them going in the reverse direction. All right. So more sodium comes in because you have more of these epithelial sodium channels, these ENaC channels. All right. And we'll come back to those channels because they're important. But as you're bringing the sodium in, you need to have more activity of the sodium potassium pump. That way you can get more sodium out and maintain that concentration gradient. At the same time, to maintain electrical neutrality, you need to upregulate the renal outer medullary potassium channels. And I don't think you need to know the name, but they're the ROMK channels, and you're going to pump potassium out. All right. So you're bringing sodium in, and the Na potassium pump is going to be pushing sodium out to maintain that gradient. And at the same time, you're pushing potassium out, and the NAK pump is maintaining that gradient as well because it's also bringing in potassium when it releases the sodium. Additionally, hydrogen can be secreted. All right, so hydrogen can also be secreted. Okay, that's all important. You need to know this. So coming back to the ENaC channels, what can happen is that there's our genetic mutations that are activating mutations that can actually upregulate these ENaC channels at different levels. There's different stages where they can act, but the point being, it's a type of, it looks like primary hyperaldosteronism, but it's still happening even when there's no aldosterone. In other words, these channels are always turned on whether aldosterone is there or not. So there's all these channels become constitutively active. All right. Okay, so this is called Little syndrome. So this is an important clinical correlate, which is why I'm discussing it here. Little syndrome. I'm gonna put SX for syndrome. Little syndrome. So what is Little syndrome? It's an activating mutation in these sodium channels. So what's that going to do? Well, if this is the lumen side, so this is the urine side, and this is the cytosol, what we're doing is that we're bringing more salt in and we're losing potassium and we're losing acid. So first of all, we'll have a metabolic alkalosis. The metabolic alkalosis. Okay, you'll have a metabolic alkalosis because you're losing hydrogen. You're going to have hypokalemia. You're going to have hypokalemia. Why? Because as you bring in more sodium, you have to lose more potassium. All right. And it's also going to cause low renin. So it'll be hyporenin. Why? Because when you reabsorb this salt from the lumen where it was supposed to be urinated into the cytosol, that means it's coming back to the plasma. You've reabsorbed this salt. So if you've reabsorbed salt, you're going to be drawing more fluid into the extracellular compartment. And because there's more fluid in the extracellular compartment in the blood, you're going to have higher blood pressure. And that increase in blood pressure is going to prevent renin from being elevated because the macula densa is not going to detect low sodium. In fact, it's going to detect high sodium. All right, so that's Little syndrome. So going back to our discussion of the fluid getting, now that we've explained what's going on here, now let's think about what's happened. So in states of low salt, what's happening is that the fluid and the salt has been reabsorbed effectively for the most part in the proximal convoluted tubule, in the descending limb of the loop of Henle, and then that's where salt and fluid. Salt is absorbed in the proximal tubule with fluid. The descending loop of Henle is going to absorb fluid. The ascending loop of Henle is mainly going to be salt absorption through this Na potassium 2 chloride symporter. And then there's going to be even more salts reabsorption over here in the distal convoluted tubule through the sodium chloride symporters, such that by the time you get over here, most of the salt has been reabsorbed. All right. So because there's not a lot of sodium getting here, not a lot is going through the ENaC channel. And because not a lot is going through the ENaC channel, you don't actually lose that much potassium. So we can see that the body has a built-in mechanism in states of low sodium and low water to sort of preserve potassium. Now, if this happens for a really long time, you can override this sort of balance. Also, if I want you to just think about what would happen if you were to use a loop diuretic such that, remember, this is a major site of salt reabsorption, all right? And or a thiazide diuretic in either case, particularly with loop diuretics though, because that is the major site of beyond the proximal tubule, the ascending limb of Henle is the main site of salt reabsorption. You can see that if you were to block this channel with a loop diuretic, you would have so much salt, and then some would be reabsorbed here, but you would have so much salt. And now there is a lot of salt to go through the ENaC channel, and this salt that does have to go through the ENaC channel needs potassium to be lost. All right, if the salt's coming in to the interstitium, potassium has to be lost in the lumen and excreted in the urine. Okay? That's important because one of the main side effects of a loop diuretic is going to be a hypokalemic metabolic alkalosis. So loop diuretics can cause a hypokalemic metabolic alkalosis. All right? So what we see is that depending on how much sodium, how bad of a deficit of sodium there is, and how able the nephron is to reabsorb sodium, there'll be a different amount of activity of the ENaC channel. All right. So what happens when there's just high potassium and everything else is normal? You don't have elevated angiotensin, you don't have elevated renin, none of that's going on. You just high aldosterone. All right. So what's going to happen is that this is not going to be upregulated. All right. This is not upregulated, and the rest of the nephron is normal, right? Function here is normal. Function here is normal. Okay, so this extra 5% of salt is not being reabsorbed anymore in the sodium chloride, or it's not that the 5% isn't being reabsorbed, it's just not upregulated. So that more salt than usual can get here. So what's going to happen? The body's going to shed some salt so that we can into the interstitium so that we can lose, so shed maybe wasn't the best word. It's going to reabsorb some salt back into the interstitium so that we can lose potassium in the urine because we have such high potassium. So when only aldosterone is active, you don't actually have that much salt reabsorption as compared to the previous example. These are not as active because angiotensin isn't upregulating them. So there is enough salt coming to the ENaC channels such that the salt will go through them, and that will necessitate a loss of potassium. All right? And that's not too important. I just want to use it to illustrate the importance of the presence of sodium going through ENaC and whether that's going to cause a hypokalemia. Another situation very similar to this is if you applied a thiazide diuretic. So what does a thiazide diuretic do? It will inhibit the sodium chloride channels. So one of the main side effects of a thiazide diuretic that you must know is hypokalemia. Why? Because more salt is going to get to this region, and that's going to necessitate more potassium being shed into the lumen to reabsorb that extra salt. All right? So that's why that's important. You got to know it. This you have to know that thiazides and loop diuretics, their main side effects that you definitely need to know are hypokalemia, especially with loop diuretics. This is most prominent with loop diuretics because as you can see, there's a big natriuresis. Natriuresis, or loss of sodium in the urine, that comes as a result of these loop diuretics, and that's what we want, right? We're giving these loop diuretics because our patient is is fluid overloaded, right? In a congestive heart failure patient, you need to get all that fluid out of them. And one of the best ways you can do that is using a loop diuretic, and you can achieve this natriuresis. However, there are a couple things you have to consider. Um, so first of all, you're losing volume, so you have decreased volume. All right, and this decreased volume as a result of the loop diuretic. So first you had a lot of volume. You give your loop diuretic, now you have a natriuresis, you have a diuresis, water goes where salt goes, there's less fluid in the body now. Well, that's detected. Remember, the macula densa is going to pick up on that after the loop diuretic has its effect. It's going to be like, yo, where's all the salt? All right? And what's that going to lead to? It's going to lead to renin. And what's renin going to lead to? Angiotensin. What's angiotensin going to lead to? Aldosterone. All right? So administering a loop diuretic will activate the renin-angiotensin-aldosterone system, and it provides a volume contraction. All right, this is called a volume contraction. So that loop diuretic provides a volume contraction, and that's actually going to be a criteria to achieve a metabolic alkalosis. Metabolic alkalosis will be will occur during a volume contraction. It's called a volume contraction metabolic alkalosis. And the reason why it's a volume contraction metabolic alkalosis is because the volume contraction eventually leads to increased aldosterone. And because you have a loop diuretic, you don't have more salt reabsorption because this isn't functional. So yes, this sodium chloride symporter might be more active, but that doesn't really matter because you've lost so much salt. And because so much salt is getting to the aldosterone sensitive distal nephron, and you do have aldosterone present, you're going to have more salt reabsorption in those ENaC channels. And that's going to necessitate loss of potassium through those ROMK channels. So, and not just potassium, but hydrogen ions. So that's where you get your metabolic alkalosis. And that's how you're going to get hypokalemia. So administering a loop diuretic will cause a hypokalemic contraction metabolic alkalosis. That is so important. And what follows is that a lot of these things are acting to counteract the loop diuretic, which means if a loop diuretic causes changes in the body that partially counteract the effect of that diuretic, you will achieve a maximum effect at some point. And the only way to get more salt loss is to increase the dose of the diuretic. All right. And typically this is going to happen within the first 2 weeks of administering a diuretic. You'll see whether a lot of the changes in the ions and the alkalosis, it's going to happen before the body has fully adapted. At that point, you need to administer more of a diuretic to get an increased diuresis. All right? And that last part might not be too important for step 1, but it'll definitely be something you need to know clinically. And I wanted to talk a bit, and this was the slide I initially wanted to draw on, but I figured while I was already explaining everything, that I didn't want to just like interrupt and ruin the flow. There is one thing I want to point out for the loop diuretic. So let's say we administer a loop diuretic, and we're like, oh God, we're going to cause hypokalemia in our patient. He's going to get an arrhythmia, or he's going to die. What are we going to do? Well, you have tools. You have tools available. What if you just blocked this? Problem solved to an extent. Doesn't solve the congestive heart failure. Um, but it does solve the issue of too much salt getting to the aldosterone sensitive nephron and causing a hypokalemic metabolic alkalosis, because you administer amiloride, which is a direct inhibitor of those ENaC channels. All right, so this is the ENaC channel bringing sodium across. Amiloride is going to directly inhibit it. All right, this is important. You must know this. Amiloride is a direct inhibitor of the ENaC channel, and it is a potassium-sparing diuretic. Why? Because by inhibiting the sodium channel, it means that sodium isn't coming back in from the lumen to the cytosol, which means you don't need to lose potassium in the lumen, and it spares the potassium from being, urinated. Another form of a potassium-sparing diuretic would be using an aldosterone receptor antagonist. So what if you block the thing that upregulates ENaC? That works too. So a drug like that would be spironolactone. All right. So spironolactone is going to competitively inhibit at that receptor, and that's also going to be a potassium sparing diuretic, because the idea is that if aldosterone can't increase ENaC because spironolactone is already on the receptor, then um, it's a moot point. Now, sometimes people will switch from spironolactone to amiloride because one of the side effects of spironolactone, particularly in men, is gynecomastia, so breast development in men. So if that happens, there are there are other drugs you can use, but amiloride does not have those side effects because it has a different mechanism of action. Amiloride blocks the sodium channel, and again, that's important because what if someone has Little syndrome? Are you going to treat them with spironolactone? No, because in Little syndrome, the sodium channel is automatically upregulated. It's called a gain of function mutation. A gain of function mutation. So by using the amiloride, what you do is you directly block this channel that has this gain of function mutation. If you were to provide spironolactone, you would not solve the issue. All right? So hopefully that wasn't too much for you guys. I personally enjoy this topic a lot, and I hope you enjoyed it as well. Take care.